In this video we're going to take a look at the optimistic challenge on HackTheBox. It's an easy Pwn challenge and the description says, are you feeling positive? So let's start by downloading the file, we'll copy it over to our local directory and we'll do some basic file checks. If you are trying to learn Pwn at the moment, you're working your way through the retired challenges on HackTheBox, I would recommend going through these videos that I'm doing in order. It's not necessarily in order of difficulty because that can be quite hard to judge because you have difficulty rating and you have the number of user solves, so you kind of have to go by a mix of those two because older challenges are likely to have more solves, but the newer challenges are likely to be rated more easy because the people who have already solved all the old challenges now find the new challenges easy because of the experience they've built up. So it's quite hard to determine exactly what the order of difficulty is. This is the order I'm going through them in, so I would recommend going through them in that order unless you've done all the other challenges and you're just simply trying to get this challenge done, in which case let's move on to trying to solve it. So let's check the file type first of all, and we'll see it's a 64-bit LSB executable. It's got Pi enabled, it's dynamically linked, so it can be used in external libraries, libc and things like that. It's not stripped, so symbols aren't stripped. We'll be able to check out function names and things like that easy enough. Alright, cool. So what else can we do? Let's have a look at the strings. Strings-n10, optimistic. See some of the imports here, some different functions. We can see some print statements and probably taking some input from the user. Here we have a printf format string where it's using the pointer format to give us a memory address, memory location, and we have some more output. So let's also run checksec then. We can do checksec. You can just do checksec optimistic, but it doesn't give you autocomplete, or it doesn't give me autocomplete. So if you do -- file, it will give you autocomplete, and we can see what we've got enabled here. So there's no canaries found. We had canaries in the last challenge, although we didn't actually need to worry about them. We have NX disabled, so we will be able to execute some code on the stack if we're able to get it there. So this might be a good indication that that's going to be our target goal, to actually get some code onto the stack and execute it, rather than some, ROP chaining or return to win and things like that. Pi is enabled, so we've dealt with Pi on a couple of the challenges. We'll show how to use Pi base and break RVA and things like that in PwnDbg, and we'll see how it affects us with the challenge. What else should we do here? Let's try and run the program. Let's do chmod +x optimistic and let's have a look at it. Okay, so if we run the program, it asks us, do we wish to enroll ourselves? Let's just say no to see what happens first of all, and we get too bad, see you next time. Let's hit yes this time then. It asks us for an email, just put in something, an age. Let's see if it even checks the age. Nope. Doesn't look like it. Length of name. Okay. Length of name. Let's say 1,000. Whoa, there. You shouldn't be too optimistic. Okay. So it crashed whenever we said that it was 1,000. Let's go back. Oh, I didn't even notice. Here's your small GIF. So that's our pointer string. So you can see that this is giving us a different address each time. So because Pi is enabled, this will give us an entry point basically into the stack and into where we can use offsets and things from there. So alright, let's do the same. Age, whatever. Length of name. Alright, well, let's say 10. 10's fine. Alright, and let's say, oh, we've got an alarm clock which is telling us to do it a bit quicker. Alright, let's do this again. We'll say yes, A1, length of name is 10, and we'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And you'll see here that we got thank you, you'll be in touch soon, but it only took the first 10 characters of our name. So it looks like what it's doing here is it's asking us the length of the name, and then it's defining that it'll only take this amount of characters from the name. We know that we can't put in too many characters, we can't put in a length that's too high because we tried 1,000 and that didn't work. So we can go through and try to fuzz that and try to find out what's the maximum length that we can enter. I wonder, let's try and do ltrace. Optimistic, yes. Email, okay. Age, 1. Length of name, 10. And here you can see then that it's doing IO scanf and it's taking in 10 characters from us. Presumably if we just say crypto, it's going to be fine. It's going to say, yeah, thank you, we'll be in touch soon. Okay, so what we want to do is try and go and find out. I was hoping it would actually see, where was the length of name field? I was wondering if it would actually show us there what the maximum available length is, but it doesn't seem to. So we can do that, as I say, through fuzzing. We could do it in through looking at the assembly code, but what we normally do at this stage of the Pwn challenges is open up Ghidra and go and decompile the code. So let's do that now. Okay, so we're going to create a new project, and we'll just call it optimistic. And we can open this up. Should have just gone to import file there actually, but we'll do that now. Import file. We'll import optimistic. Okay. Yes. Analyze. Okay. Just hit defaults to everything. And we get into our code here. So because it's not stripped, we don't need to worry about searching for strings or just going through the functions to try and work out what's important. We can go straight to the main function. So what do we have in the main function? We have some variables declared here of different types, some undefined, chars, int, unsigned int. We have some buffers here as well on the stacks, an array of chars here, 96 bytes, local 68. So let's go and see how these variables are used throughout the code. So we have some puts calls at the beginning. This is just printing out, would you like to enroll yourself? And then we obviously need to, if you don't provide yes, it's going to say too bad, see you next time. And then it's going to set this local 79 variable to highlight that and see what that is. Oh, okay, to n, to no, okay. So then we have, if presuming we say we do want to enroll, it's going to say, great, here's your small gift. It's going to give us this point at this location. So what's this actually printing out to us? Well, we can have a look here at the code. We have, here's just, where is it? Here's your small welcome gift. Okay, so here's the small welcome gift, and this is the printf call. So before the printf call occurs, we have our arguments being placed onto the stack. So if we go and have a look at the calling conventions, let's see, actually we might be able to just highlight the printf here. Printf char, okay, so it has the EAX. It doesn't, okay, it's not showing the full. Let me grab a link and just look at the calling conventions. So we can see here the registers are used for 64-bit are RDI, RSI, RDX in that order. So our first parameter is going to be the RDI. So we had the RDI, RSI. So the RDI is going to be this string. And let's verify that. We can see that, yep, that string was loaded into the RDI. The second argument is going to be the RSI. So if we go back, oh, where's it gone? If we go back here and see the RSI, we'll see that the RAX is moved into the RSI. So what's in the RAX? Well, just before that, the RBP is moved into the RAX. So whenever this is called, this pointer location is pointing to the RBP, which is the base pointer of the stack. So using that, we'll later be able to find the offset to our stack pointer and other things if we need to. And there's a variety of ways we can do that, so we'll look at that later. So then it asks us to provide our details. It asks us for an email, and it's going to read this in. It's going to read in, so we can actually only put in 8 characters maximum for our email. And then similarly for our age, it's going to take in 8 characters. And then it's casting these to these other variables, local C, local 80. We have, it asks us for the length of the name, and this is where it's going to, let's have a look at this. Okay, so it's going to take in as a decimal the value local 84, and then it's going to check that our local 84 is less than 64 in decimal, and if it's not, then it's going to say you shouldn't be too optimistic. So that was the problem whenever we put in a value of 1000, it said you shouldn't be too optimistic. So we know then that if we go back and run this again and say yes, A1, length of name 65, I'm going to get, oh, shouldn't be too optimistic. If we go back and do that again, and say 64, then that's fine. We can now enter in a name of up to 64 characters. If we go back to our code, we can see here then that it asks us for the name, it does this read call, and we can see then that it's taken in the file descriptor in the as the first parameter, which would be the RDI. It's taken in the buffer in the second parameter, the RSI, and then it's taken in how much of that buffer it wants to read with the third parameter, the 84. So that value that we just put in, 84, that's going to determine how much of this, how much of the name to read into this buffer. And that buffer, the local 68, we know is 96 bytes. So there is no buffer overflow vulnerability in terms of that. It's allowing us to read 64 bytes into a 96 byte variable, so that's not going to overflow. But what's this other segment of code going on down here? So after it reads our name, after doing this conversion here from on our length that we provided, it reads the name, it resets local 84 to 0. Local 84 was the number that we provided for the length, and then it's going to say while true, it's going to loop through, and first here it's checking the size of the name that was read in, essentially the number of characters, and if the size plus minus 9, so if the size minus 9 is less than or equal to 0, then it's going to return and say thank you, we'll be in touch soon. If not, then we'll jump down to this statement here where we're checking either 1 is equal to is alpha, so it's checking is the character alphanumeric, and it's checking int local 68, which is our buffer here that we've read the name to, local 68. If the local 68 and the local 84th element of it is alphanumeric, then if it's alphanumeric and it's within the range of 9 and 48, then we will increment the loop counter and we'll keep looping through doing that. So essentially it's looping through, as long as we can get past this condition, it's going to loop through each of our characters and just make sure that each character is alphanumeric and within the correct range. So that's something we're going to need to bear in mind whenever we're trying to put together some shellcode. So now we've got a general idea what's going on with the code here, let's talk about the actual vulnerability. So we have this local 84 variable, which is an unsigned integer up here, and then whenever we use a local 8 variable, we read into it, we convert it to an int. So we're converting between an int and an unsigned int. Well, we're converting from an unsigned int to an int, and then we're doing this comparison. So this is where the potential vulnerability can arise with a integer overflow. Let's go and have a look at what that is. Let's just go back here as well. So it's converted to an int to do this, to check the condition here, and then when we get back down, it's then converted to an unsigned long, and then we convert it back to an int. So yeah, let's go and see what the issue is with that. So I'll throw a link to this article in the description, and this describes how integer overflows happen. So in most programming languages, there are a certain amount of bits in memory. For example, space reserved 32-bit integer data types may store an unsigned integer between 0 and over 4 billion, or a signed integer between minus over 2 billion and plus over 2 billion. In the case of signed integers, the most significant first bit usually signifies whether it's an integer is positive or negative value. So essentially, when you have a unsigned integer, say it's 8, say you're using 8 bits for it, you would be using every one of those bits to describe the length, and that's how you're able to get it up to over 4 billion. If you were using a signed integer, the first bit, the most significant bit, will indicate whether it's negative or positive. So only the next 7 bits are used for the value, which means you don't have as big of a value, but you have the same range essentially. Hopefully that makes sense. So the problem is, whenever you try to perform calculations, here it gives an example of the maximum size of an unsigned integer. If you add +1, a lot of compilers and languages don't deal with this properly. They'll wrap around and it'll often result in a 0. Results can be even more unexpected for signed integers, so whenever you go over the maximum value of the signed integer, the result usually becomes a negative number. For example, over 2 billion plus 1 is usually minus 2 billion. And when you go below the minimum value, underflow, the result usually becomes a positive number, for example, and then it gives this as an example. So you can have a look at this, have a look at some of the risks and an example of this in action. But essentially, what we're hoping we might be able to do is go and supply a negative number here for our name length, and then whenever it goes to do this comparison, it's going to say, is the value that we've provided below, what was this value again, 64? Is it below 64? If it is, which it will be because it's going to be a negative number, then it'll pass that check. But then when we get back here, it's going to convert it back to an unsigned variable, an unsigned long in this case, meaning that it will essentially go back to a large positive number. So let's go and try and put this together. We'll play around in GDB PwnDbg first, and then we'll go and put together a PwnTools script. So we'll boot up GDB PwnDbg, pass in optimistic, and as usual we can have a look at our functions in here. Oops. We can have a look at our functions. We can disassemble functions. If we wanted to have a look at the main method in here, we can have a look at that, no problem. See that the addresses haven't been populated yet because it's using Py, and they're not going to be populated until the program loads, and they'll be different each time. But the offsets remain the same. So just before we start to play around this, let me just note that we can use PyBase. We're not able to use it just yet because the program's not being run. Let's set a breakpoint at main, and then let's run the program, and then let's check PyBase. And you'll see here that the base is this value, and we can also use the break RVA as well. Let's do PyBase -h. So PyBase, and we can say PyBase and then the offset as well. So we could give in PyBase, and then let me, as an example, say if we wanted to set a breakpoint after this puts call, we might say PyBase and then provide this as an offset, and then this is going to essentially it's going to add the two together and give us the correct offset. We can do something similar with break RVA. Let's do break RVA help. Break RVA from PyBase, and we'll basically just say the same thing. Instead of saying we want to find out the location of the instead of saying we want to find out the offset of this puts call from the PyBase, we just say we want to set a breakpoint there straight away. So we could say break AVA, paste that in, RVA, sorry, paste that in, and then that's going to straight away just set a breakpoint at that location. So this can be pretty handy in PwnTools to go and set up breakpoints whenever Py is enabled, because each time it's going to be a different value, but you won't need to worry about that. All you'll need to know is what is the offset from the, from in the function that you want to get to. Okay, so I'm gonna delete the breakpoints. In fact, let me just run that for now. I'm gonna hit continue at this point. Would we like to enroll? Yes. And here it's asking us, it's giving us a small welcome gift. Why don't we hit Control and C to get out of here and have a look and see what this address is. So the address was, we could go x over, we could just do print, or let's do x over, we can print this in different formats. You could say x over string, x over character, x over x for like the hex address. Let's do that, x over x. You could say 100x, and it'll give you all the different values here. But essentially, the value that it's leaked out here, 0x7fff, what is it? Let's have a look. And you see right here the RBP. That's exactly what it is. So we knew that already because we saw that the RBP had been set up here. The RBP was placed into the, right down here. The RBP was placed into RAX, the RAX was placed into the RSI, and that was the parameter to, but we could have also identified using a breakpoint in here, so just wanted to show that that's possible. Okay, cool, and let's try and hit continue. We got the alarm clock. Is that going to cause problems for us? I think it will do. Let's do, oh, I meant to do that. Ages, the length of name is -1. Alright, so we do that -1. It just says thanks, we'll be in touch soon. let's try and run that again. Yes, a -1, and it just crashes out, be in touch soon. Okay, let's go and try this here. We'll do /optimistic yes a -1, and here it actually asks us for a name. You see that? Let's try and put in a name above 64 characters, and you'll see that we've got a segmentation fault. So it looks like we've overwritten the instruction pointer there, so we found our buffer overflow and we found out how we're going to want to exploit it. Let's go and try to put together a PwnTools script to get this done. So I'm going to take a copy of the PwnTools template I have here and just call this exploit.py for now. We'll open that up. And as usual, we just need to go and make a couple of changes. We'll set our exe to optimistic. It's going to grab the context for us, so it'll take care of the architecture, the bits, the operating system, things like that. Let's set our context level to debug so we can see a bit more output. This is where we might want to put some break RVA statements if we wanted to break. So let's just say, if we were to go back, let's open up radar. We'll open up radar, optimistic. We'll do AA to get the functions. We will do AFL to list them. And then we'll say smain and then PDF to disassemble. And there might be somewhere here that we want to put a breakpoint. So it asks, where does it ask for the name here? Oh, there, you shouldn't be too optimistic. Okay, so yeah, it's asking for the name around here. Let's copy that, and we can paste that in. So we can set that breakpoint up. That will set a breakpoint at this offset from the pi base once the pi base has been identified. This is only going to run if we type in, if we add GDB in capital letters to the end of our call from a command line. Alright, something else we need to do as well is just make sure we're using the correct architecture here when finding the instruction pointer offset, so we can change this to use a 64-bit addition because we're going to be reading from the stack pointer instead of the program counter or the RIP. And that's about that. Let's take this out for now because we're going to be looking to try and get a shell, so we'll just say IO interactive, say got shell, and we're going to be sending the payload here, but we'll put all this together later. Let's have a look at getting this offset first of all. So the offset, we're going to need to look for probably a bigger offset because we know it's 96 bytes anyway for that buffer, as we saw up here. So let's try and change that. We can change it, it doesn't really matter, but let's do 500. And then we're going to need to try and plug in the values here. So I'm not too sure why it didn't allow us to do this in GDB, so we wouldn't have been able to do the cyclic pattern in GDB because whenever we put in a -1 value it simply didn't ask us for the name. Let's now, oh, not here, we want to send it in with a payload. Let's have a look at the output again. Let's close this down. We'll do /optimistic. It asks us, do we wish to enroll ourselves? So we can just say after the first colon we're going to say yes. Okay, and then it's going to ask us for an email, so we can just copy this. We could just look for the colon again, but I like to just put in some of the text as well, just so you can see, looking through the code, what it's actually asking you for. What we enter here doesn't really matter too much as long as it's below 8, as long as it's 8 characters or less, otherwise it's going to overflow into the next parameter. Not as a buffer overflow vulnerability, but just it's going to put some of what we enter into the next field where it asks us for the name, is it? Let's go back here, hit the alarm clock again. So it asks us for the age, then it asks us, alright, so we'll just run through that. Age is next. And again, as long as it's below 8 characters, should be good. And then length of name. I'm going to put in the full thing just so I can see again what's being asked, and then let's do our usual then in our name. First of all, we'll say 64. That's the maximum length that it allows you to enter, and then it's going to ask you for the name. Oh, I should have just copied this. Okay. Going to ask for the name, and then that's when we would send our payload, which is going to be our cyclic pattern of 100 bytes. So, should we try and run it and see what happens? We run that, we get non-type object has no attribute read, so it didn't find the core file because it didn't dump a core file because we didn't overflow the buffer, because we said that the name length was 64 bytes and the buffer takes up to 96 bytes. So let's try it now with our -1 value, which didn't work for us in GDB. We'll go back here, we'll change this to -1. We'll run that again, and this time we get this back saying it's located the EIP/RIP offset at 104. So this makes sense. Essentially it's saying that, let's go back to our code, we have the 96 bytes here, so if we write 96 bytes into the buffer, they're all going to be fine. Then we write another 8 bytes, and then after that we're at the instruction pointer. So that makes sense. We've identified the offset, which is good. Let's go and try put together an exploit here. Okay, so let's go back to our code. Let's uncomment this. We're going to start the program now. We'll comment all this actually. And I'm going to change the format of this slightly because this is looking to say at this offset inject this, but we're going to actually want to place our shellcode into the stack first. So if you go back and look at our code, we have this variable, the 96 bytes, and essentially that's what we're going to be writing. So we're going to be writing, we can write our 96 bytes of shellcode, or 104 bytes of shellcode, because that's where the RIP then was. We can write the shellcode, and then we can write the return address, and the return address we want to set to jump to the beginning of that shellcode and execute it. So let's go back here. Let's first of all, we want to grab we need to identify the location of the EBP which is leaked to us. So whenever this starts, let's go, we can take this right here, io.sendLine after, and that's going to get it started. We want to leak the stack address. I'm just going to take a copy of the code that I've used in the past couple of challenges where we've leaked this, and in the ROP Emporium series. So let's look at this. It reads the lines received back, which will be, let's do this quickly. It's going to read all these lines, and it's going to, using regex, it's going to extract this memory address. Okay, it's going to then convert it into base 16 and into an int, and then we're going to print out the address here. So if we, let me just change this. Oops. So if we run that now, we'll do Python exploit, and we'll see that this is come back. It says leaked stack address, and it successfully extracted that address from our from what was printed out there. Okay, so that's done. Our payload then. So our payload, well, let's go and build up the full structure here. So we're going to be sending this afterwards. We're going to build our payload. We're going to send this off all the exact same, apart from we need to change this to IO. We can actually, let me change occurrences, IO. Oh god, no, not all. Okay, forget that. I'll just do this manually. You could have just highlighted that all as well and done it in selection, but oh well. Okay, it's going to send off the payload, and the moment our payload is empty. So what are we going to put inside our payload? So we're going to have, in here we'll have our shellcode. We need some padding, so our padding can be, we can just use a cyclic pattern. We can say cyclic offset. We could also use, normally I would use like a no operation instruction there, but because we know from the code that if anything in there is not in the alpha, it does not meet this condition, is alphanumeric, then it's not going to run. So we'll do cyclic and we'll say the offset minus the length of the shellcode. As long as the shellcode is less than the offset, this should be fine. And then we can send in our stack address. But the problem is our stack address at the moment is going to be pointing to after this variable. We want it to point back 96 bytes. So we can go back and say minus 96. And that looks good to me. All we need to do is build up our shellcode. So we know that we can execute code on the stack. Let's try and just generate as we've done before using shellcraft. So I can do shellcode equals, we'll do ASM because we want to compile it into the assembly shellcode, and then we want to pass in shellcraft dot, and we can pass in different functions here. Unfortunately you get no autocomplete, so if you want to check out the options, we can do shellcraft-l in the command line. We can do shellcraft-l grep linux and get an idea of what we can use here. If there's something we want to use, we can say this is thumb, so not this one, but we could say shellcraft and pass that in, and you'll see that it takes at least one argument, so we needed to actually pass in cat and then flag.txt, and then it'll produce that out. We can then say -f and give it whatever format we want. Let's say raw. See there, if we do -a, it'll give us the assembly, and etc. For us, we're going to be using the AMD64 shell, but we can just get that in here, and we don't even need to specify AMD64 or Linux because it's all been done for us whenever we defined this context right up here. Okay, so we've got our ASM shellcode done. Let's run this and see what potential issues we might run into. So we'll go back here, do Python exploit. It runs through. Oh, there's the issue we're going to run into, that we've got a typo. Let's go and change this to cyclic. Run that again. And you'll see it's gone to interactive, but we got this end of file while reading interactive, so whenever we put something there, it's not actually going to work for us. And without doing much debugging, it'll be pretty clear what the issue is here. So we have our shellcode here. This isn't all alphanumeric characters as it should be. So we need to try and fix that. Now, I ran into a lot of issues trying to do this, so I'm going to run through some of the issues that I ran into, and then maybe that'll help. One, clear this up for anybody else who tries to do it and runs into the same issues, and also maybe somebody will be able to tell me if I've done something wrong, or if there's a different or cooler way to do what we're going to do. So let's go and look at trying to encode this shellcode into alphanumeric inside of PwnTools. So if we actually go to, let me just go and Google here, PwnTools encoders, and we can have a look at some of the documentation. You'll see the first thing that we see here is this encoder alphanumeric, and it says it'll encode the shellcode raw bytes such that it does not contain any bytes except for capital A, lowercase and uppercase, alphabet, and 0 to 9. And it accepts the same arguments as encode, which accepts the bytes that we want to encode, the raw bytes, the bad characters that we want to avoid, an expression, so any regex we want to use to match bad characters, and then we can force to re-encode even if it doesn't contain invalid bytes. So there's a lot of different options here. We have printable, we can do XOR as well. Plenty of different options, but let's see what happens if we try to do this in PwnTools. Let's go back and let's say shellcode equals alphanumeric, and we'll see here if we go to this, we can see that it takes in our raw bytes, and yeah, it takes all the same parameters. If we want to go and have a look at this, we can just follow it through and go and have a look at the code and see what PwnTools is doing. So it's returning encode on raw bytes, and it's using this expression alphanumeric. So we can actually go and have a look at that expression. And this is pretty handy because I was struggling to find documentation to show exactly how to format these expressions. And I was having a lot of problems in general with encoding, which we'll see more of in a minute. But this means that you can go and try to combine some of these. So, for example, we could take, in our case, alphanumeric. It needs to be alphanumeric and less than 59, 57. So we could put this in here, and then we could also say, okay, and it must be within bytes 0 to 57, obviously in hex form. So that's pretty cool. We can obviously put in different regex and stuff as well based on this format. But if we go back here and test this out, let's do shellcode alphanumeric. We'll pass in shellcode, and what I'm going to do here as well is just we'll print out shellcode, and then we will print it out again here. And if we try to run this now, Python exploits, you'll see we've got an end of file error there. Let's try and run that again. Okay, this time it actually got to this stage with the shellcode, but you'll see that the shellcode looks exactly the same, and these definitely aren't all alphanumeric characters. If you go and put some of these in, they don't map to characters at all. And if we look here, we'll see that there's actually no difference at all in what we've printed before and after. So I spent a long time trying to work out what was going on here, and trying with different forms of encoding. I was, instead of using alphanumeric, I was using encode, and then manually specifying regex and things, and just nothing was really making any difference. Eventually I determined that it's due to a Python 3 issue. So if we do if I do source PwnTools, I'll activate my Python 2 environment. You can just run Python 2, but just make sure you have PwnTools and things like that installed. I'd recommend using Python environments for doing that. So now if we run python exploit.py, we'll see it runs through, and it does actually attempt to encode it, but we'll see that there are no coders for AMD64 which can avoid using only alphanumeric for this code that we have in here. So what else can we do? Well, I tried a couple of things here. Let's open a new window. Let's do msfvenom. So msfvenom can be used to generate shellcode, generate payloads, and if you've done I'm doing a lot of challenges here, but if you've done more like HackTheBox boxes and vuln hub and things like that, you'll probably have a bit of experience at least with using these payloads in combination with Metasploit and things like that. So we can specify, for example, msfvenom, we can do -l payloads. That'll give us a list of all the available payloads quite slowly. You'll see that there's plenty there. If we want to say, alright, we want to grep out Linux, we can have a look at the Linux only payloads. We should have really grepped out Linux x64. So a lot of these are for reverse shells and things, but we can use this Linux x64 exec and then say we want to exec bin sh or bin bash or something like that. And we also have encoders here, so we can do -l encoder. If we can spell it, we can do it. And we can list out the different types of encoders. And notice that for x86 we have these alpha upper and alpha mixed, but we don't actually have anything for 64 there. We have XORs, but XORing is not necessarily going to get us alphanumeric characters. So we could let's try and put together a payload anyway. Let's do msfvenom dash we'll do -f for format Python, just to say that we want to print it out in a way that we can just copy and paste it straight into our Python code. And then we can do -p, we'll do Linux x64 exec. You can specify architecture and platform and things like that. Typically you don't really need to, because it's gonna define a lot of that based on the payload and stuff that you select. But let's just do it here, just to show what we can enter here anyway. We can do platform, say Linux, and then what's the command that we want to pass to the exec function. In this case, we'll say bin/sh, could say bin bash or whatever. And in this case, I'm going to do the we don't have many options, so I'm going to do the alpha mixed for x86, even though we're doing a 64-bit payload. Let's see what happens. And we'll see there the selected arc is not compatible. Let me go back. And this prints out. So this is interesting. It's it's going through the x86 alpha mixed, but it's doing it for a 64-bit payload. So yeah, I mean, maybe it's pretty obvious that this isn't going to work, but let's just, for the sake of it, let's go and paste it into our code. We'll put in here the buff. We can select buff here and then go to change all occurrences and change that to shellcode. And then this is just going to be our shellcode here. This is obviously all alphanumeric characters, but there is a problem, and there's no point me even really running this. Let me just run it and we'll see what the problem is. We'll do Python exploit, and we'll see there it stopped. Okay, this slice. Essentially, we can go back here, but let's print out length shellcode, and let's print out the length of our offset. Not length because it's already in int. Let's print out our offset. So here's the issue. Our shellcode is 156 bytes, and our offset is at 104 bytes. So if we write 156 bytes, we're overwriting the return address as well. So our shellcode is too long, essentially. So even if that was possible to work there, it's not going to work for that reason. Let's go back and say, what about if we do this, and instead of doing the encoder, let's just print it out. You see there it was 156 bytes, 7767 for the size of the Python file, 156 bytes. Now it's 47 bytes. So now it's less than, this was over three times the size for the encoded version. So what I was thinking here is, well, why don't we take this and paste it over here. Again, we can change all occurrences and say shellcode, and then we can just say, well, shellcode should be equal to alphanumeric shellcode. Now if we print out those lengths, let's go back, and we'll see that, did it even print the lengths? No. Okay, so it just basically said there are no encoders for AMD 64 which can avoid using the which can avoid, this is confusing, the double negative. There are no encoders which can only use alphanumeric characters to encode this. So we run into the same problem. So this is really unfortunate. I'd really like to know of a cool way to do this, just using PwnTools and using msfvenom or something. But essentially, I ran into a dead end here. So I will demonstrate instead how I solved this. Let's take out all the shellcode that we put in, and let's resort to Google, and we'll say we want to find a Linux alphanumeric small shell. We want something that's able to encode it but is within a good range. So we have packet storm security here we could look at. I also found, let's just say shellcode. We have exploiTdb here. Oh, I did find a, let me see, GitHub. Yeah, this Alpha 3. I actually downloaded and tried to use this before realizing that it's also only for x86. So it seems to be for x64. There's just a lot more problems getting this done. So we have packet storm here anyway. Here's some assembly code. This is the ASCII string for the shellcode for that. And then similarly we have one here on exploitDb. You can see here Linux. Oh, this is x86. Let me go back. x64. We'll go to exploitDb. It's normally a good source. You probably spent a good bit of time on this if you do the HackTheBox machines or have done OSCP or something like that. And we can see then the code. You can have a look and see what they do, how this is being done, or we can just grab the assembled 87 bytes, which is a perfect number for us. We can go in here and say our shellcode is equal to, and then just paste that in. Oh, what did I open there? Oops. Shellcode, and that's looking good. What if we try to run it? Do we have a end of file? No. So what if we try to list? And it's all looking good. So if we had a flag in here, presumably we'd be able to cat our flag. There's no such file or directory. So that's looking good. Let's go and test this against the remote server and see how it goes. I'll put these links in the description to everything that I bring up in the video. And let's start this now. Grab a copy of the addresses. Because we're using this template, we can just paste this in, remove the colon. Oh, and we also need to say it's remote first, so just say here remote in capital letters. Run that, and we don't get a shell. Oh, there we do. Okay, so the first time that didn't work for some reason. Let's try and list the directories. Yeah, and we're able to list the directories. We're able to see that we're logged in as root, and of course we are able to cat the flag.txt. And there we go. I hope you've enjoyed this video. Hope you're enjoying this Pwn series. If you have any questions, comments, you can leave them down below. Thanks.